Well, hi everyone. Welcome to the modeling tutorial for the week. My name is Melissa Wrzesien. I work in the Hydrological Sciences Lab at NASA Goddard, and I'm one of the co-leads for this tutorial. The other being Brendan, if you want to say hey.
Sure, yeah. I'm also based at NASA Goddard Space Flight Center. I'm a contractor with a company called Science Systems and Applications Incorporated. And the both of us work on a team called Land Information Systems modeling framework. And so we'll learn a bit more about that as we go through it today. And I guess before we get too ahead of ourselves, I also just want to give a shout out to Jian Lee for his help in putting together our notebooks. And of course, a shout out to all the Hackweek folks for putting all this together and all their support throughout the way.
Yeah, it's definitely, thank you for the support, that's for sure. Very cool. And I guess I'll go ahead and start and say, we will be monitoring the Slack channel, but feel free to unmute and interrupt us as we go. We probably will hit our about 45 minutes, but we're also happy to cut something if we get some questions in the discussion. That's totally fine. So yeah, welcome to the modeling tutorial. Today, in particular, we're going to be talking about the NASA Land Information System, or LIS. However, I really think everything that we present will really be applicable to kind of like any model output that you're working with, especially if you're working with NetCDFs. So while we are demoing how to interact and visualize LIS data, it's certainly applicable to other models that you would be interested in running. So yeah, we'll jump right in. So just what is LIS? So if you aren't familiar with LIS and if you've never heard of it before, it's kind of this broader software framework, which the ultimate goal, I guess like any model, is to get the best estimate of land surface states and fluxes that we can get. But really what's cool about LIS is that it combines land surface modeling and data simulation all kind of in one package. So we have this too long didn't read. You don't get anything else out of today, just having a basic understanding of what LIS is, where it's this tool that can combine land surface modeling and data simulation. I think if you understand that, then you can progress, and that's great. But what I think is really great about LIS, and I guess hopefully the font size of this is good. I zoomed in a little bit. Interrupt me if you want to see larger fonts. But in my opinion, one of the most important and most useful aspects of LIS is what we've written down here. It's just that it's incredibly flexible and it's really designed to meet users' needs. And meaning that it's really all about these different plugins and these different modules that come together into just one system. So this diagram here is basically a pictorial form of what we have in this paragraph, but really the central component of LIS is the choice of land surface model, and that's what's shown here. So as opposed to maybe you're running snow model, or maybe you're running NoNP offline, LIS has a bunch of different land surface models all in it, and it allows the user to choose what they want to best suit their particular model needs. Beyond the choice of land surface model, it has choice of net data, so down here in the bottom left, Mirror2, and LDAS, all these different things, and new net readers are continuously being added to the system. And then as I mentioned up above, data simulation is a really big component of LIS. So maybe you want to assimilate soil moisture from SNAP, or snow depths from Answer 2. LIS is built to do that already, again, all within one framework. I think there was a project maybe last year, maybe it's in review, that they assimilated snow depths from ASO. So it's not just satellite data, there's some airborne, assimilate ground data. And this framework makes it so that that LIS has all these different applications. So some are detailed here in this diagram, but just, again, it's all user-based. So if you have a particular study that you want to design, likely LIS could help fit that. So current effort, well, I guess I'll say, you might notice a lot of these land surface models oftentimes aren't necessarily designed to be run. It's super, super high resolution. In my experience with LIS, the finest that we've run for a project is 1 kilometer, which if you're thinking continental or global, 1 kilometer is great. But if you're thinking in terms of wanting to know detailed snow processes, 1 kilometer is quite coarse. So if you want to get a good simulation of what's going on over Grand Mesa, 1 kilometer might not cut it. So there are current efforts in the LIS team, to implement snow models into LIS, one of which is Snow Model, Glenn Liston's model, also Crocus. So these are ongoing efforts. They're not in the public version of LIS just yet, but they are certainly coming. And we've been testing simulations with these down to a scale of 100 meters, and in some cases even finer than that, which I think will be really powerful and really important for snow modeling purposes. As we say here, it'll enable the simulation of wind redistribution of snow. I believe Crocus simulates snow grain size in numerous layers. So these are some really exciting things that are coming. And I guess I'll also say, even if you're not interested in any of these land surface models, but you are interested in maybe running your own model, but you need really good net data, one nice thing about LIS is that it is pretty computationally efficient. Like, it's been designed to run well in parallel, runs quickly, and there are processes built into LIS for downscaling met data. So maybe you take NLDAS2, or you have WRF output, but it's too coarse for what you're hoping for. There are processes within LIS to downscale that data to a finer spatial resolution. And kind of along with the efforts of Snow Model, we're, in addition to implementing the snow component of Snow Model, Micromet, which you've maybe heard of, is being also implemented, and it'll be able to be used with other land surface models and other, like any MET data. So you might be able to take NLS2 wind fields, downscale them with Micromet, and then use it with NOMP, for example. So I think that's one nice aspect of LIS, where maybe you're not concerned about NOMP, but you want better MET data. LIS might be a tool for that. So let's see. Yeah, developed by the Hydrological Sciences Lab at Goddard. Specifically, Sujay Kumar has done a whole lot about this, and I would say he is super expert. If you have any questions, he can answer it in like 10 seconds for you. He has a lot of knowledge about this. But we do provide extra links. I think I have a few open. The LIS website, which I do want to point you to, even if you still have more Git questions and you want more examples, we do have a working with GitHub, I don't know what this is called, page. We've been working with GitHub page on Git, which I find very useful as a newbie to GitHub. Of course, the examples will all be like LIS focused, but you can transfer that to other things. And then here's just a link to the LIS GitHub page in case anybody is interested. I guess stop me if are there any questions on kind of the basic overview, high-level overview of LIS. If not, I don't see anyone unmuting, so I'm going to continue. So what we'll be talking about today is understanding how we can interact with model output that is like output that comes from LIS. So in this particular case, NetCDF model output, and then demoing how you can compare it to other raster data and point data. We have a note here that while this particular simulation was output into NetCDF, it's been converted into what's called a ZAR store. Brendan will talk about that more. He is far more of an expert on that than I am, but it's better for cloud computing purposes, from what I understand. So the LIS simulation that we've shared with everyone today is this larger model domain over the Mississippi River Basin. We're sharing a period of 2 water years just to limit the amount of data we're sharing. So we do have it for longer, but we're sharing 2 years of it. I would say it's a pretty moderate resolution simulation, 10 kilometers. But I think that'll be a nice way to have something that runs pretty fast when we're interacting with the model output. But again, you can run this finer, if you wanted to design a LIS simulation. NOMP forced with MET data from MERA-2, and I think our precipitation is from the GPM satellite mission. And we're actually sharing here, we're going to be demoing an assimilated simulation. So this took snow depth from SNODAS and assimilated it into NOMP. And then for the data sets that we'll be comparing to, for a raster comparison, we're looking at SNODAS, and for a point comparison, we're looking at SNOTEL. I'll start with SNOTEL because I know earlier in the week, David demoed how to interact with SNOTEL data, how to download it like on the command line from NRCS. We provided a link to that. In case you need remembering, the SNOTEL network is hundreds of automated stations that are kind of sprinkled in mountains across the western US. In this case, we're going to be looking at snow depths, or speed, one of the two. And then the other data set, which I can't remember if this has been discussed this week, SNODAS, or the Snow Data Assimilation System. You can think of it as like a model that does pull in some ground observations and some airborne observations, but it's produced by NOAA. We provided a link where you can download it if you're interested. It's only available for the lower 48 though. So before we move on to the notebook with Brendan, does anybody have any questions at the moment of what I've gone over so far? I see a thumbs up from, okay, so I guess I'm good to go. So I'm going to, let's see, I'm going to stop sharing. And Brendan, you can take it away with the notebook. So if everyone can go into their Jupyter Hub, and we'll be able to walk through the notebook together.
All right. Thank you, Melissa. Can I get a thumbs up if you guys can see my screen, just so I have some confirmation? Sweet. Thank you, everybody. Yeah, thank you for that great intro, Melissa. So in case you don't have it open just yet, just a reminder on the Jupyter Hub, we're going to dig down into the website repo, books, tutorials, lists, and we've got two notebooks here, the ones that start with 1 and 2. So I'd recommend opening up both of those. And another thing that I'm going to recommend here, just so we can sort of speed through this a little bit more, we're under a bit of a time crunch. You should go up here to this Run menu option here and click Run All Cells. And so what that's going to do is just going to execute everything in the notebook as we work through it. There are a couple places that take 30 seconds, 2 minutes to run or something like that. And so this will just help us move a little bit more quickly through the notebook without having to wait for those things to happen. So without further ado, let's jump into it.
Hey, so Brendan, really quick, can you zoom in just a smidgen? I have really bad eyesight.
Sure. Let me know. Is that better? I can go a little bit more.
That's better for me as long as it's still good for your viewing.
Yeah, it should be fine. Yes. Thanks. So yeah, just a reminder. Okay, yeah, can say the same thing. Maybe I'll go up to 200%. Why not? All right, so Melissa gave a brief intro to the list output. As she mentioned, list can write a couple of different formats, GRIB, NetCDF, some proprietary binary that we came up with. We're shifting over to NetCDF output for the most part, since that's standard in most places these days. When you develop your simulation in list, you can select the frequency at which you output data. So you can be writing 6 hourly, daily, monthly, whatever your heart desires, really. So the output that we're going to be exploring today was generated as daily NetCDF files. So every simulated day, a NetCDF file was written with all the variables that we specified that we wanted in the output. A bunch of small NetCDF files don't necessarily work as efficiently when we're dealing with cloud-hosted data. So we converted these into what is called a ZAR store, which is a newfangled data type that's being developed for improved performance in the cloud. And I keep mentioning the cloud. Just like this Jupyter Hub is running on AWS, we've decided to host the data that we'll be using for this tutorial in an S3 bucket, because on the NASA side, we're also exploring how to better leverage these cloud-based storage and computational resources that are in vogue at the moment. So fingers crossed everything works, but it should. So let's go ahead and jump into it. First thing, of course, we're going to do is to load some libraries, import some libraries that we're going to be using throughout the tutorial. The first one that we're going to load is this S3FS, which is an interface to the Amazon S3 file system. We're going to use that in a few places just to open individual files, such as the CSVs and text files that the SNOTEL data is stored in. The next libraries that we're going to load is NumPy and Xarray, which are used for interacting with ND arrays. I think you may have heard something about these libraries earlier in the week. Next ones we're going to load are pandas and geopandas. I don't think we actually use geopandas. I think that's just stuck around as I was developing the notebook. So don't worry about that one too much. It's just a sort of a little brother to pandas that adds some geospatial functionality. The next couple of libraries that we're loading are these plotting libraries, HoloViews, GeoViews, and some extenders or accessors for pandas and X-ray, which will allow us to more easily plot directly from objects that come from these libraries. And then the last thing that we're importing is a distance function that we use in a helper function later to grab the nearest grid cell location to a given lat-long point. Sort of a hacky kludge to get the grid cell that we want, but it works. So we're going to stick with that for today. The last thing that we do here is we set the Bokeh library as our plotting backend for HoloViews. So this will allow us to make some neat little interactive plots. So don't see any questions in the Slack, which means I think I can go ahead and continue. So the next thing that we're going to do now that we have our libraries loaded is we're going to go ahead and load the list output. As I mentioned, we're hosting this list output on an S3 bucket for a project that we're currently working on. And so one thing that we do up top is we create this reference to the S3 file system. We're just letting it know that this is how we're going to access the bucket itself. The bucket is named EIS-DH Hydro, has a subfolder called SnowEx Hackweek, which our data is in. So we're just going to store this in a variable up top so that we can use that throughout the notebook to access data within some subfolders in there. That's sort of what we do here. We build this path to the list output is in a ZAR store, has this funky name, but this is just from the list naming scheme. Whenever it outputs data, it just follows this. So we stuck with that when we were putting it up on S3. The next step for opening some data on S3 is to create a key value store or map from our path to the actual object on S3. And then what we can do is we can use this variable list output mapper right here in our open ZAR call to load the actual data itself. We pass this argument consolidated equals true because what we've done when we created this ZAR store is we wrote all the metadata describing the structure of the data set itself into a little file that sits at the top. So instead of reading all of the data at once, Xarray will actually just read that metadata file, and whenever it needs to go and grab the actual data, it will do it at that point. So it's sort of called lazy loading as opposed to eager loading or eager behavior. The last thing that we do is we drop some variables that we don't really need. These were added when we were creating the ZAR store, and they can kind of mess a few things up. So we just drop those up top so that we don't need to deal with them. I have a question in the Slack. So if we're doing this outside of Hackweek, do we need different code to read the netcdf files? So it's actually very similar. If you're reading multiple netcdf files, Xarray provides this open multi-file data set function, and then what you would do is pass it a list of the netcdf files, just like that. And you can even pass a argument like this, parallel equal true, so that Dask knows to sort of take over when reading all of this. So that's a really great question. Thanks for asking. So since we've run the notebook already, the data set itself is actually loaded. So let's go ahead and explore it. We can quickly inspect the data. You may have seen this earlier in the week when interacting with Jupyter Notebooks. All we have to do is type the variable name in a cell and execute it. And when it comes to Xarray or pandas, there's some built-in functionality that creates this nice little HTML interactive inspection widget. And so we can kind of explore what this data set looks like. We have a couple dimensions to the data set. The first one we see is soil moisture profiles, east, west, north, south, and time. So we have a 4-dimensional data set in some cases. But for the most part, it's actually just a 3-dimensional data set. We have an X, Y, and a time dimension. This soil moisture profiles dimension only affects one of the variables, the soil moisture in our output. So there aren't 4 levels to each variable that we have here. Currently, we only have one coordinate dimension, and that's time. We can see that it runs from October 2016 to September 2018. If we click on this little drop down here, we'll get a list of all of the variables that are contained in the data set. So we can see we got a ton of stuff in here. 26 or 27 different variables, albedo, leaf area index, evaporation, canopy evaporation, snow water equivalent, all sorts of fun stuff. And we can see the dimensions that each of these data sets have, or variables have rather. And so we see down here on the soil moisture one, we get an additional dimension on that. Each of the data sets that we have here also has some attributes associated with it. So if you click this little document, you can see some additional information about that particular variable, such as the long name, which isn't too different from the standard name. We also get some units. We get some vmin and vmax, which are kind of bunk values from the looks of it. Not sure if that's propagated from the netcdf or if that's just from the ZAR conversion itself. If the data set was a bit smaller or we loaded it all into memory, if we clicked on this icon here, we would get a preview of the data. In this case, we get a look at how the data is chunked for parallel reads. So it's just a little overview of what each chunk of the data looks like and how big it is. So don't need to worry about that too much at the moment, other than to say that that's a product of us sort of lazily loading the data at the moment. We can click on this attributes tab, just like we did with the variables, and we get to see some global attributes for the data set, such as the X resolution, the Y resolution, and these are in degrees, the map projection, you know, more stuff like that. Southwest corner latitude, longitude, website, the CF convention that we're adhering to, a reference, the land surface model used, and some other stuff there. So now that we've interactively accessed some of the elements within our data set, how can we access them programmatically? Well, we can access the attributes of our data set by accessing this .attrs or attributes. And if we run that, we get the same thing that we saw here, just printed out in a Python dictionary. So if we wanted to access any one of these elements, we could go ahead and do that in the standard Pythonic, dictionary access way. So for example, if I wanted to get dx, I could add that here and we'll get the dx value. So if we wanted to interact with any of these attribute elements, we could certainly do that. Variables are accessed the same way, but there are two different approaches that you can use. I suppose you could use these also for accessing the attributes, but I think it comes up more frequently when dealing with variables. You can use this dot notation where you call the variable for our data set dot and then the name of one of the variables that it contains. So in this case, since it's a SnowEx tutorial, we're going to focus on the snow variable. And so if we run this cell, we get a glimpse at the snow depth variable in our data set, which looks exactly the same as if we had gone up here, clicked on our data variables, gone down to snow depth and clicked on this guy right here. So it's just giving us a peek at the structure of the data in memory at the moment. Another approach is to use this square bracket notation where it's sort of like accessing elements in a dictionary. Gives you the same exact output as the dot notation. So you might be asking, which syntax should I use? They both perform the same function generally. But I would say that the square bracket syntax is a lot more useful when you're interacting with data programmatically. So for example, we can define a variable called varName, which holds the string of the name of our variable of interest that we want to get out of the data set. And then we can put that inside the square brackets as opposed to just writing the string itself. So if we want to write a loop that loops over all variables, or if we want to write a plotting function that takes the variable name in and then plots a particular variable that we pass it, this is a good way to do that. The dot notation won't work the same way because if we try to, in this case, create that variable name, snow depth t average string, and then we try to access it with the dot notation, what Xarray is going to do is it's going to try and look in the data set and find a variable called varName. It's not going to go and look at this variable varName and pull that string out. So if we run that, we're going to get an error, basically says there's nothing in this data set that matches that variable name. So the next thing that we're going to talk about is dimensions and coordinate variables. Xarray is sort of similar to NumPy, if you have any familiarity with that, in that it deals with n-dimensional arrays, but Xarray puts the labeled in labeled n-dimensional arrays. So instead of having to remember what your rows and columns all represent, you can add these labels and metadata. And so Xarray calls these dimensions and coordinates. The dimensions are the labels for each dimension in the data set. So time, for example, is one of our dimensions. And then coordinates provide labels for indexing along those dimensions. So we can pass, a particular date if we want to go grab it, as opposed to indexing or selecting via the index integer. So if we wanted the first time step, we'd say time equals 0. But when using coordinates, we would use something like time equals a particular date of interest. So using these labels, it's a lot easier to subset, slice, aggregate, etc., the data set that we're working with. So now we can get a look at what that looks like. If you're familiar with pandas, the LOC and the ILOC functions, Xarray provides pretty similar functionality for their data sets as pandas does for their data frames. Index selection is performed using this .icell for index selection. And as I mentioned earlier, we can select by the index number. So the first time step in Python is going to be at 0. Whereas if we want to select by value, the actual label for a dimension, the coordinate, we would just use the .sel select function there. And instead of passing the integer, we pass the label that we would like to select. So let's take a look at how this works. Selecting the first time step in the file. We run this cell. Comes up, there we go. We basically get a single slice of the file. So we've lost one dimension since we're only dealing with one time step. And we can see that we preserved some of the other coordinate variables. So we still have the label that this is the time step for 2016-1001. We've got the lat lon because it's still a 2D array at this point. And we still have all the variables. It's just for that first time step. We could also select by a particular date. In this case, we're selecting by January 1st, 2018. And the output looks very similar. The only thing that's really changed here is the date. We're also capable of using shortcuts and when we're using the select function. So if we just wanted to select the entire month of January, we don't need to specify the entire date or a range of dates. We can just say 2018-01, and Xarray intelligently pulls out or slices the date dimension for us. So now we see we've got 31 time steps, the month of January available. Does it always say dimensions soil moist profiles because that's the highest dimensional data variable? I'm not really sure, to be honest. I don't want to pretend that I'm an expert in Xarray and all this stuff. I'm still learning how to use this, so I'm not sure why it picks that one to go first. In some cases, it doesn't necessarily do that. So something to find out. Thanks for asking.
Do you think it picks that one first because it's a capital letter and then the others are all alphabetical?
Ooh.
Like it's alphabetical capitals and then alphabetical lowercase.
Interesting.
That might not, but it is. It maybe just happens to be that way.
Yeah, it's an interesting theory. It just might. Okay. So yeah, we grabbed the whole month of January. If we want to do a custom range of dates, we can use this built-in Python function called slice. And then we put in the labels that we would like to slice from. So if we wanted the first 2 weeks of January as opposed to the whole month, we can select using that slice variable and we get just what we're looking for. So at the moment, you may have noticed that latitude and longitude are listed as data variables, and I'll just show you guys down here. They're buried down in the data variables. But they're not among our dimensions or coordinates for this data set. This is just the way that the netCDFs were written, coming out of lists. It's something I think we're probably going to change at some point because we've brought that up. it makes it a little easier to work with in Python. I think a lot of folks on our team use grads and MATLAB and things like that, where it may not affect them as much, but as we move towards using Python and R and things like that, it might be nice to have lat and lon up top. But for this tutorial, we're gonna have to do that ourselves. So I've written this little helper function here to do that for us. And what it really does is it goes into the attributes of our data set. It pulls out those dimensions, the spatial dimensions, converts them into a float because they're stored as strings, gets the grid cells and the X and Y dimensions, and then the lower left lat and lon, and then builds an array of the coordinate values for the data set, and attaches them back to our list output. So if we look here, we still got the east, west, north, south dimensions. After we run this cell and after we run this one here that applies this function to our output, we can see that we've now got lat lon in our dimensions and our coordinate values. So it'll make it a lot easier for us to slice and subset along these dimensions within our data set. It's kind of a hacky way to do it. You might be asking why I don't just go ahead and grab lat and lon from right in here. It actually turns out that those fields contain NaN values, not a number of values, and trying to append those directly to a data set as new coordinates makes Xarray unhappy. So I had to do it this way for whatever reason, but it's something that we hope to work out in the future. Anyways, now that we've got our soil moisture profiles, our lat lon, time dimensions, we've got everything looking good, we can now use labels to start slicing along the lat and lon dimensions, so do some spatial subsetting. So in this cell right here, I'm using the slice functionality. Oh yeah, Megan Mason, can I explain part of the helper function? Sure. So this is a little, I think it's a Python 3 thing that you can do, and it's called type hinting. Basically what we're saying is that this function expects an Xarray data set to be passed into it, and it's going to return an Xarray data set on the way out. If when you're writing your code or the execution, something happens where an integer or a string or something is passed in, it's going to throw an error and say that this is not the right type before it actually tries to execute anything. Same thing on this side here. So this is a little nuance of Python 3 that I stuck in here. It doesn't really affect anything super seriously. We could take all that out and just put data set here. But I've been trying to learn some new Python 3 things as I go forward, so figured I'd give it a shot. But thank you for the question. So we've added our lat long coordinates and dimensions, and now we can do some spatial subsetting here. So we're going to do some crude subsets. We're just going to slice roughly the bounds of the state of Colorado here. So we're going to say that we're slicing along the latitude dimension, longitude dimension, and these are the ranges of lat and long that we want to slice across. So when we run that, we see we go from 215 by 361 grid cells to 40 by 90, but everything else stays just about the same. If we want to subset across multiple dimensions, we just did 2 dimensions up there. We can also add in time as well. So if we only want water year 2018 for the state of Colorado, we can pass that in as well. So here we're selecting across time, latitude, longitude, and at the same time, we're using the square bracket notation to select just the snow depth variable here. And we're storing that in a variable that we've called snow depth, Colorado, water year 2018, DS. And so you may see when working with Xarray, people end their variable names with _DS. This is just an indication that it's an Xarray dataset object. Some folks, when they're working with pandas data frames, will use _DF as well, just to give that indication that it's a data frame. And it's a nice little helpful reminder when you're working through this stuff of the object type. The interesting part about this that I'm just noticing now is that we're actually dealing with an Xarray data array, which is another type of object coming out of Xarray. So perhaps this should actually say DA rather than DS. There's a little bit of difference between a data array and data set. I don't want to get overconfident and say that I know exactly the difference, but typically a data set is built up of data arrays, and you can sort of jump between them, but generally they work in roughly the same way. There are some functions that are provided for a data set that don't exist for data array, but you just have to dig into the Xarray documentation to really understand all of that. So we've got our snow depth T average over Colorado for a single year, that water year 2018. And so far we've really been looking, quote unquote, looking at the data through these HTML inspection widgets, which isn't the most exciting unless we just want an overview of the shape of the data itself. Thanks, Joaquin. So the next thing that we want to do is probably look at some plots. So we've imported two plotting libraries. The first one we kind of imported, not explicitly, I guess, implicitly, and that's Matplotlib, which I think has been used throughout this tutorial so far. And this is really nice for generating really quick static plots. We've also imported HVplot and HoloViews and GeoViews, and these are good for generating some interactive plots. So the first thing we'll do is we'll look at a Matplotlib static plot. So what we're going to do is simply use this .plot function on the Xarray data array that we've created here. But first, we're going to go ahead and select just the first time step. We don't want to pass a whole bunch of time steps into the plotting function. I think it wouldn't be too happy with that. It probably wouldn't know what to do. We could do that, but we'd have to specify how we want Matplotlib to handle those multiple time steps. So we could say something like, make a bunch of rows and columns for each time step or something like that. But for simplicity's sake, we're just going to select the first time step, go ahead and plot that. And this is what we get, very simple, basic plot. If we want to change, the title and the color bar label and the X and Y labels, we can certainly do that. But it's a big old rabbit hole of the Matplotlib documentation that you have to dive into, but it is totally possible to customize just about everything about this plot. This is just showing how we get a generic plot nice and quickly. Similarly, we can make an interactive plot using the HVplot accessor and specifying the quad mesh type. So that's the type of plot that we need to use when we're dealing with gridded data. So similar to what we did above, we're just going to select that first time step. We are going to use the HVplot accessor, and then we're going to say from within HVplot, let's make a quad mesh type plot. We then pass in some arguments here. So it's a little more complicated than the Matplotlib approach. We pass in a geo equals true. We're just saying that this is geolocated data, and it's going to go and look for Latin long when it plots, and it also allows us to plot it on a base map and things like that. Rasterize just means to render the data set before plotting it, as opposed to plotting the raw data. You can get a bit of performance improvements out of it when you're zooming in and out. Project just goes hand in hand with the rasterize function. And then in order to make our plot look similar to that Matplotlib plot, I passed in some labels for our axes and specified the same color map that was used above. So you can see that these plots look really similar. The only difference here is this one is nice and interactive. We can hover over and see values at each time step. We can zoom in and out nice and quickly. So it's pretty cool to be able to explore your data in this way. Unlike Matplotlib, we can also pass multiple time steps into HVplot, and it will intelligently give us a time slider to play around with it. So it's a little cramped on my screen with it this big, but we can see that we now have this time slider that will allow us to sort of scroll back and forth in time. And it's not super snappy. It does have to go and pull the data and render it and all that. So it can be a little slow when it's running, and the changes are fairly subtle unless you really, drag around quite a bit. So from here on out, we're just going to stick with that HVplot plotting as we go through the rest of the tutorial here, just because it allows us to do some pretty nice things really easily, combining different plots in a layout or overlaying them with each other. So now that we've plotted, individual time steps and mapped those, let's look at how we can make a time series plot from this data. So first thing that we're going to do is we're going to define a set of coordinates from within the data set that align with a particular grid cell, just so that we can select that grid cell and then plot the values for that across the time dimension. So all we really need to do is select from lat and lon, those latitude and longitude variables that we defined up here. And then all we have to do is call HV plot. So since we've reduced the dimensions down to just that one point, there's no longer a two-dimensional array that we have to worry about for plotting a gridded output. So HV plot knows that, hey, this looks like something I can plot as a line. So I'm going to go ahead and do that. And I did something a little fancy here as well. I created a layout, which is HV plot terminology for combining plots side by side or above and beyond, or above and below each other. And then I also did an overlay over here. So on the left, we see the time series for that particular point. On the right, we see a map with a point indicating where this time series is taken from. So this is an example of sort of the cool stuff that you can do with HV plot and hollow views. So now that we've done a single point time series, we can learn how to create a time series over a broader area, so we can aggregate, across a rectangle or something. In our case, we're going to look at, how to aggregate over this Colorado dimension or domain that we defined earlier. So that's right here. This is that data set, water year 2018 over Colorado. And all we have to do to aggregate over that is call the mean function or method, and then specify the dimension that we want to aggregate over. Same thing goes for max. And then down here, it looks complicated, but it's basically what we did above to plot the quad mesh. There's just some arguments that I've passed there to add some little flourishes, such as a title and the base map, things like that. And so what we've got here is our mean snow depth for water year 2019, max snow depth for water year 2018 side by side. So it's really super easy to aggregate and subset and do all that fun stuff with your list data, or any raster data that you can get into an X-array object for that matter. So if we want to do an area average, so instead of averaging over time to get the average at each grid cell over the year, we can take the mean over a particular area to generate a time series. So instead of just doing one point like we did earlier, we can do the mean snow depth over Colorado for that water year 2018. So the way that we do that is, instead of specifying the time dimensions, I'm going to add in my hint here for the argument. We're specifying a list that contains lat and lon. So it's going to average over those two dimensions as opposed to the time dimension, which will remain. So we can see here in this output that we only have one dimension now of 365 time steps. We've retained the labels for all those time steps. And then it's super easy again to plot that time series. So we just call HV plot, pass in some arguments to add the flourishes, and we get this nice interactive time series plot that we can zoom in on, and we can see the individual values and all of that. So now that we know how to do all of that stuff, it's time to compare some list output, which is what we were talking about up at the start. So first on the docket is comparing our list raster with our SnowDAS raster. So the first thing, of course, that we've got to do is load our SnowDAS data. Looks very similar to what we did for the the list output. The only thing that changes is the path to the data itself. So again, to ZAR data, we've stored the metadata, so we can say consolidated equals true. We use the open ZAR function right here. We pass in the mapper. Same exact sort of process as what we did for the list data. I just kind of condensed it into a single line as opposed to separating it out as we did above. Another thing that we have to do with this SnowDAS data is apply a scaling factor to it. This comes from the SnowDAS user guide. And so we just apply that right here. It's super easy. You just multiply the data set object itself by the scaling factor, and voila, Xarray knows to convert all of the data values by that factor. So I mentioned earlier that we imported that distance function from SciPy to help us find the nearest grid cell to a given lat long point. This is right here. I wouldn't spend too much time worrying about it, but this is super helpful for pulling out a grid cell given a lat long point. This will work for our LIS output. This will work for our SNODAS output. And the reason that we kind of have to do this is because the SNODAS output and the LIS output are of different resolutions, and so when we try to pull out, a particular lat long grid cell in LIS output, those same labels won't necessarily work for the SNODAS output. So we have to get the appropriate latitude and longitude to grab the grid cells. So diving into this should look fairly similar to what we did earlier to create that single point time series from the LIS output. In this case, we're just using the SNODAS data. So the first thing that we do is we use that NearestGrid function that's defined right up here. We pass in the SNODAS data set that we loaded, and then we pass in a tuple containing the longitude and latitude that we defined earlier in the notebook. And so what this is going to do is return a latitude and longitude of the nearest grid cell in the SNODAS data set that we'll be able to use to extract a single grid cell's time series. So another thing that we're going to do is define our start date and end date for the plots. This is, we could do the entire data set, but it'll take a little while. So I'm using a smaller chunk of data. So the first 3 months of 2018, there's 2 months, I guess. And I'm defining just a plot date range with a slice that we can then pass in when we're selecting a data set. So we're slicing from the start date to the end date. Makes sense. And then all we need to do is to create a subset data set by selecting for our longitude, latitude, and then our plot dimension, which is what we defined right up here.
Hey, Brendan. Just so you know, we have like 5 minutes in case we want to have a little bit of a break before the time lapse.
Yes, sure. Yeah, so I'll skip to the end. I added a bunch of comments in all this code so that if you guys want to explore it later and figure out what I'm doing here, you can go ahead and do that. So basically right here, we create the subsetted data sets. So basically the single points from LIS and the SNODAS. We create the time series plots right here, SNODAS and LIS, and then we overlay them here. So this is kind of I do want to mention this is a HV plot thing. If we want to combine two plots on the same axes, we just multiply them together like we're multiplying two numbers together. If we wanted them side by side, we could change this to a plus symbol and they'll appear side by side. So when we run all of this, this is what we get out the back end. We get this interactive plot where we're comparing the LIS and SNODAS output, and we can see that they agree pretty well for the same general area, which makes sense because, as Melissa mentioned earlier, this is a LIS simulation that assimilated the SNODAS data, so you'd expect it to be fairly similar. The next thing that we're going to look at is the SNOTEL point comparison. This is a little more complicated, so and given the amount of time we have left, I don't want to jump all the way into this. But again, I added a bunch of comments that sort of explain what's happening here. All of this is really just going in and grabbing the information from the SNOTEL text files that we've got, loading those up, and then creating a plot. And it just so happens that the time series plots that we've been making, this latitude and longitude, refer to a site that is contained in SNOTEL. I think it's the Bear Lake site. And so we go ahead and we grab that Bear Lake site, we convert it from centimeters to meters, and then again we multiply the Bear Lake plot times the LIS and SNODAS plot, and so now we get all three of them on the same plot. So We can see that list and SnowDAS agree pretty well, but SnowTel is a little different. You know, it's a site versus 10 kilometer and 1 kilometer data. So we would expect them to be fairly different. So sorry to rush through the end of it there, but you should now be, you know, a little bit more familiar with working with list data and generally just rasters in Python. And I think the code in this notebook is a really nice jumping off point for developing some more advanced comparisons and widgets. With that in mind, I'm going to jump over to this second notebook here. We didn't plan to run through all the code in this. We shared this with you guys as sort of like an aspirational, here's what you can do if you really dig into this stuff. And I will say that the main developer of this notebook was Jian Li in the Sisto group here at NASA Goddard. And we can just go ahead and scroll down because what we have in this notebook is a really neat interactive, two neat interactive widgets for exploring list data, SnowDAS data, SnowTel data, all in one. So we scroll down, we'll get to this interactive widget where you can select the state that you want to view. It plots all of the SnowTel points within a particular state. We can compare snow depth and SWE. You can select a start date and an end date. And to see the time series, you just click on one of the points and it will take a few moments, but it will pop up eventually. This is just sort of some slow performance because it's going to grab data from two different raster data sets. And we're still working on getting those structured appropriately for fast time series analysis. So while that's loading, I'm just going to scroll down just a little bit and show you one more thing. This is what the list output looks like for the entire domain. So this is another interactive explorer that we can use to look at this data. You can select the variable of interest here. We have a time slider that will allow you to pan back and forth in time. It's a little buggy. We're still working out the kinks on it, but it's a neat way to explore your data. If I scroll back up, now we can see that we've generated the plot comparing lists, SnowTel, SnowDAS, all in one. So I definitely recommend that you play around with this, explore it, look at the code. I've tried to put in a bunch of comments explaining what it is. It's definitely complicated. It's kind of like that meme where it's like, how do you draw an owl? And it's two circles and then a fully drawn owl right next to it. But it's just to give you an idea of what's possible with these libraries and Jupyter notebooks and hosting data on the cloud. And so with that, I think we're happy to answer any questions if there are any. If not, thank you for tuning in and have a great Hack Week.